is. Honestly, the difference between a university and college, it's just basically time and money.
Okay. But if you like a student in a college and go for apply to a job, that still is good evaluated or not? They're
Well, it
gonna say
depends
like,
on the
oh
job.
no,
That's
you
the
went to
thing.
a college, you know?
No, that's the thing. It depends on the job. If the job has a prerequisite that says like you need an associate's degree or higher, or a bachelor's degree or higher, it depends on that. That's the entirety of what it depends on. So like if the job requires, say, a master's degree in something, then it's probably like a specialized field position, and you have
I mean,
gone
I'm
to a
just going to
university.
be a nursing, no anything like a.
That's not so bad. Yeah, no, that one's just like I think a bachelor's and some certificates, if I remember
Okay.
correctly. I can't.
And we have that program. So we don't have a lot of bachelor's programs. Wait, I'm not sure if we have a bachelor's in nursing or not, but you can get certified to be a nurse through SVC. So we have a nursing program where you can do all of your training to become a nurse.
I mean,
there are
but
people
when
that get
when I'm
bachelor's
going
degree,
to apply to a job and say like I get my degree in Skagit Valley College, it's gonna be good or it's gonna be
Yeah, no, they don't care where you got the degree as much unless they're really
okay.
snobby people.
What they care about is your experience, like
clinical
internship.
hours.
Yeah, and clinical hours. Thank you.
And the clinical hours, during going to do it in some point with the college, or is just by myself?
Well, you'll have to do some probably before you get into the nursing program. And then after that, they'll put you into practicums. I can't remember what the exact term for it is, but yes, you have experience to do work in inpatient care, but not as a nurse yet. So yes.
If you haven't yet, you should meet with an advisor. That would be your best route because they can plan your whole learning path for you.
Yes, I need that.
Do you know who your counselor is?
What are you talking about?
Okay, Luce, you and me got some stuff to talk about after this recitation.
Who helped you plan your courses? Who helped you enroll for courses?
Okay, the person that
I'm going to interrupt here because Luce, you're in first quarter experience, and that's going to happen during that class.
What?
You're in a first quarter experience class, and that's what we do during that class.
Okay.
Okay.
You're in the process of learning all this right now. All right. You'll come out the other end a changed person. It's great.
Yeah. Okay, let's gonna talk about chemistry.
I like chemistry.
Yes.
I'm much better at chemistry than I am nursing. I have a lot of nursing students who have graduated on my watch over the years, like hundreds of nurses at this point.
I've noticed that a lot of the people in this class are in the nursing program.
121 is one of the big feeder courses for pre-nursing.
Yeah,
so,
and
yes,
it's funny.
That's every quarter. Almost all of my students are pre-nursing somewhere.
I just think it's funny because I want to work with dead people, not living.
They don't talk.
Oh my god.
They don't complain as much.
Hey,
they
nice.
don't.
They don't talk back.
No, the worst that happens is you get some unwanted flatulence and some unwanted skin slip, and that's about it. If their makeup doesn't stay, that's because you didn't use the setting powder. Like,
what?
So...
Animals don't really talk back either.
Wait, do you have questions, Mr. Musk?
Doctor. Issues. I'm having issues. Give me just a second, okay?
Oh, okay. I wasn't sure if the what was for me.
No, it was for, I'm trying to share my screen and trying to have my document camera do what it's supposed to, and nothing's working right today. All right, this should be okay now.
I feel you. My word, yesterday it was working just fine. Today it's saying that it expires in 4 days. And I downloaded it off of SVC yesterday.
I don't know, maybe that's weird. I don't know. 4 days? The month doesn't end in 4 days.
Quick check.
That makes...
Quick check. I would like you guys...
I contacted IT. They said that they'd call me within an hour. They never did.
Oof. Sorry. Sorry, Mr. Musk. I know I derailed the class.
I want you to give
So
me an
do
electron
I.
configuration for, let's do arsenic.
Oh, that song. Okay.
Give me the full one for arsenic. All right.
Oh.
As in no shortcuts.
Oh.
Okay. Question.
Good. Well, hold on. I'm not done yet.
Okay.
And then after that, I would also like you to give me the full shorthand electron configuration for gold. Let's not do gold. Let's do silver, Ag. And I'll let out of the bag that silver has an anomalous electron configuration. All right. So quick practice with those two concepts. And then we will move on to sort of the end of chapter 2 / beginning of chapter 3, which is what does this electron configuration mumbo jumbo teach us about how atoms behave? All right, how atoms behave.
I have a question.
Yes.
Is this for a neutral?
Yeah, neutral. So they have
Okay.
not lost or gained any electrons. When we
that's
get to
an
chapter
S.
3 and talk about gaining and losing electrons, then we can talk a little about what electron configurations look like for ions, but we're not there yet.
Oh, okay, cool. That's good to know. So what is that, an S or an N?
AS, arsenic.
Okay, thank you.
Remember, we can literally read the electron configuration off of the periodic table by looking row by row at what blocks that we go across. So in the first row, there's only 2 elements. We know that in the first row, there's only one kind of subshell, an S subshell, and we can put up to 2 electrons in that subshell. In the second row, Remember, every time we begin a new row, we begin to fill a new shell of electrons. So we fill in a block of 2 and then a block of 6. So that block of 2, we know a block of 2 represents s electrons, and a block of 6 represents p electrons. So 2s2, 2p6 is our second row. In the third row, again, we have a block of 2 and a block of 6. So beginning a new row begins a new shell of electrons. So we're filling the third shell. And we're putting 2 electrons into the s subshell in the third shell. We're putting 6 electrons into the p subshell of the third shell. So at the end, we've got to get through this fourth row, or not all of it, but almost all the way through it. So we go across this block of 2, this block of 10, and then halfway across the block of 6. When we get to the fourth row, at the beginning of the fourth row, we're beginning to fill in the fourth shell of electrons. So that block of 2 is part of the s electrons, the s block. So 4s2 are the next 2 electrons we put in. Blocks of 10 are the d block. We're filling electrons into a d subshell. Now remember, this is the place where you're going to screw up if you're going to screw up. That d subshells start happening in the third shell, not the fourth shell. So the first d subshell that we fill is the 3d subshell. And d subshells can hold up to 10 electrons. Finally, we have 3 more electrons to put into this configuration. We've already filled the 3p subshell, so the 4p subshell is the next one we're going to fill. Remember that block of 6 is a p block. Anytime we're going across that block, we're putting electrons into a p subshell. So we need to put 3 electrons into that p subshell to finish out our electron configuration. Okay, second checkup from yesterday. And I apologize for not having gotten yesterday's video uploaded yet. Like, today has been nonstop meeting mania for me today. So I even had to duck office hours early because it was like one meeting after another. So if you needed more time with me and I wasn't around, just stick around after class and I'm happy to spend some time answering questions. Okay, so next thing. Silver is known to have an anomalous electron configuration. What is its electron configuration? So what I'm going to write first is the wrong electron configuration. The one that we would do if we just followed what our normal rules for the periodic table tells us about how to fill in electron configurations. All right. Now, as a shortcut, we can put in brackets that silver has all the same electrons that krypton does. So that last noble gas in the row before where silver is. And then we just have to fill in the 5th row. All right. So it looks like we cross this block of 2 and then 9 of the elements in the block of 10. So that looks like 5s2, 4d9. That is not the correct electron configuration for silver because it's not normal, it's weird. That's what anomalous means. It has a weird electron configuration. So what is the correct electron configuration for silver and why is it like that?
So it should be 5s1, 4d5.
4d5? So we went from 11 electrons in those 2 subshells to only 6.
40-10.
Okay.
Sorry.
So we haven't gained or lost any electrons. All we're doing is shifting where they're at. All right. There are 11 electrons in these 2 subshells at the beginning. We still have to have 11 electrons in there at the end, or we've just like erased some electrons. That's not good.
Yeah, I think I was doing half and half.
So in this case, half and half is one way that you could end up with an anomalous electron configuration. Now, if we look here, 5s2, that s subshell is completely full. The d subshell is not full or half full.
Okay.
Remember that full or half full subshells have that special stability, right? In this case, the S subshell is half full, that's fine. The D subshell is now completely full. So that's better to have a half full and a full than it is to have one that's full and one that isn't full or half full. So that is the correct electron configuration for silver, which is anomalous. All right. Remember, you don't have to memorize which ones are anomalous and which ones aren't. I'll ask you on the test by saying X element is known to have an anomalous electron configuration. What's its electron configuration? All right. Any more questions about that? So you guys should be pretty stinking well equipped at this point to tackle the chapter 2 topics in ALEKS. Even though chapter 2 isn't the current objective yet, like start nailing those. All right. You've got a little time before the chapter 2 assignment is due in ALEKS, but there's no reason that you can't get it done like tonight and then not have to worry about homework for a while. Or even start thinking about chapter 3 and getting ahead. Imagine that. Are there any ALEKS topic questions in general, like anything from ALEKS that you would want to look at? I'm trying to make that a common ask every class so that people don't get lost with ALEKS and feel like they can't ask for help, because you can.
I just finally caught up and finished chapter 1 last night or today, whatever. So, and I
Did that last
vaguely,
topic make sense after the couple of them we went over together?
oh, with what we did in the office hours, yes.
Good.
That totally made sense. Once I wrote down those 2 extra notes to keep track of which one goes on top and which one goes on bottom. Other than that, yeah, no, I'm still taking a couple seconds. I haven't started quite on chapter 2 as much. And
It's
what you
not even
just
the
did-
current assignment yet. When is chapter 1 due again? I can never remember my due dates.
Friday.
I just
Friday.
Friday.
at n-
Yeah, so it's
midnight.
not even the current assignment yet, but that doesn't mean that you can't work on it, right?
No, I get that. I'm gonna
Covered,
work on it.
We've
gonna
covered
work
more
on
or
it.
less all the important stuff in chapter 2 in recitation, at least practice wise. We can talk kind of in a bridge for between chapter 2 and chapter 3, what these electron configurations mean in terms of how elements behave. All right. So
Wait,
in
can
chapter, go ahead.
Can I ask a really kind of simple basic question because I
Yeah.
haven't watched anything? I'm just trying to piece this together. So electron configurations are if you had, say, a picture of a molecule and you have a nucleus, and then the numbers are the number of electrons.
You're talking about
on-
an atom, right?
Yeah,
Okay, you said molecule. Sorry.
my bad.
I'm just asking because words are really important, right? All right, so atom, and we're talking about the parts of the atom. Go ahead.
There's the nucleus or whatever, and then there's the rings around it, and the numbers are each ring filled up with the number of electrons, right?
Well, that's kind of the Bohr model. All right, so let's do an example together of aluminum and then talk about how that Bohr model with the rings compares to an electron configuration. So seeing both of those may benefit you.
I'm very much a
specifically.
visual person, so I'm just very confused right now.
Yep. The Bohr model, it helps some students and it confuses some students. So let's look at both of the models together.
I'm
and then
very
we'll see how
confused
they
too.
compare to one another. Right?
I don't understand anything. Sorry.
No,
It's all
no,
right.
it's okay, Luz. We're all here to learn. It's a safe space.
So what I want you to do is for every aluminum ever, as long as it has the same number of protons as it does electrons, in other words, it hasn't gained or lost any electrons, what
Because
is
we don't have the
aluminum's
Philosopher's
electron
Stone.
configuration?
Sorry.
Aluminum's electron configuration, because it's element number 13, it has 13 electrons if it hasn't gained or lost any, should be 1s2, 2s2, 2p6, 3s2, 3p1. Now, you may not be as fast as I am at that, but hopefully you can get there by looking at the periodic table step by step. Luz, if you're not there yet, then we just started looking at this last night in recitation. So it is in the topical videos, but in terms of practicing it, we only started practicing last night. And after class and today, I have not had time to upload that video yet. I'll get it uploaded before tonight's over with, but it's like, unless you've gone through all the topical videos for chapter 2, which ideally would be great, but if you haven't yet, then you shouldn't have seen this in a recitation, because the only time we looked at it was last night.
Unless for some random reason your high school did this in your class.
Yeah, but they never talk about it the right way anyway.
school,
They
but that was
shortcut it
like
because the high school teachers
15
never
years ago.
understand why the subshells are actually important. So anyway, now I'm disparaging
My high school
teachers.
teacher had me do it like that. And
They
and
had me do both
in
the models.
in Miss
but-
Potts,
All right,
in the-
let's get back on track. So
Sorry.
what I want to do now is, now that we have the electron configuration, I want to look at the Bohr model for this particular version of aluminum, aluminum 28. Now 28 is the mass number of this aluminum. So that's its number of protons that are positively charged and neutrons that don't have any charge. That's the total of both of those, all right? So every
hold up.
aluminum ever in the history of the universe has exactly 13 protons, because that's the atomic number of aluminum. So that must mean that this particular aluminum, because it doesn't have a charge, has 13 protons
And 15 neutrons.
15 neutrons, but we're going to do the electrons first. So we know that because it doesn't have a charge, it has to have the same number of protons and electrons. Because its protons and neutrons have to add up to 28, that's why it has 15 neutrons. So the nucleus of the atom, the stuff in the middle of the atom, all right, which is a very, very small part of the total volume of the atom, contains the protons and the neutrons. Those are in the nucleus.
Yeah.
As a matter of fact, some really dorky physicists sometimes refer to protons and neutrons collectively as nucleons, the subatomic particles that are in the nucleus. All right. I actually really like that word because it sounds cool, but nobody knows what you're talking about unless they're a physicist. So if we're drawing a picture, a Bohr model picture of aluminum, all of the protons and all of the neutrons, and I am abbreviating proton P plus and neutron N0 based on their charges, all of those are found in the nucleus, that small part of the mass at the center of the atom. And remember, electrons weigh almost nothing, so the nucleus contains almost all of the mass that's in the atom. Outside of that nucleus are the electrons. So let's think about where the electrons are in aluminum. Well, these numbers refer to which shell the electrons are in. So if we organize based on shells, this is the first shell, the one that's closest to the nucleus. This is the second shell further out from the nucleus, and this is the third shell even further still from the nucleus. So we can count how many electrons there are in each one of those shells by looking at this electron configuration. In the first shell, there are only these 2 electrons. So we can just make tick marks for those. In the second shell, there are these 2 electrons and also these 6 electrons. The S and P subshells are parts of this second shell. So altogether, 8 electrons in that second shell. Now, this is one of the reasons why I don't like the Bohr model, is because it leaves out the fact that the shells are divided into parts. But if we're keeping track of how many total electrons are in each shell, the Bohr model is a simple way to do that. So how many electrons would I be putting into the third shell of aluminum?
3.
3.
3.
Those 2 electrons in the S subshell and that 1 electron in the P subshell are all electrons in that third shell. So importantly, and this is a great bridge to what we're discussing today, this third shell is the outermost shell of electrons for aluminum. All right. It's not the outermost shell for every atom, but for aluminum, that's the biggest shell that has any electrons in it. We often refer to that as the valence shell of electrons. The reason why valence electrons, or the electrons in the outermost shell, are really important is because valence electrons, the ones in the outermost shell, are the ones that are almost always involved when an element reacts with other elements.
Sorry, I just remembered something from my previous chemistry class that I actually learned.
And again, this is in the chapter 3 topical videos. It's kind of a bridge topic between chapter 2 and chapter 3. If you didn't get it in chapter 2, we talk about it in chapter 3 because learning how many valence electrons an atom has, it's really important for us to be able to figure out how that atom behaves. All right. So what I want to do is I want to look at shorthand electron configurations for a number of different atoms on the periodic table. And the reason why is because the shorthand electron configuration always gives us the information about the valence shell of electrons. All right. That last row that you fill in always includes all of the valence electrons that are in that atom. So let's talk about germanium. And tin. Let's talk about potassium.
K.
K. And magnesium. That's potassium, BT dubs.
I was making a bad joke.
Let's talk about sulfur and bromine. So what I want is a shorthand electron configuration for each one of these. We don't have to draw the Bohr model, all right? As long as you realize how this electron configuration gives us that exact same information, just in a different format, all right? It's the same information, you just have to know how to look at it. So where do those 3 electrons come from in the third shell of aluminum? They come from those 2 s electrons in the third shell and that 1 p electron in the third shell. So in total, aluminum has 3 valence electrons, right? 3
Yes.
electrons in its outermost shell. So give me a shorthand electron configuration for each one of these atoms, and then tell me how many valence electrons each of them has. And I'm going to add one more to the list just to be a dink. Let's do titanium.
I thought you were a dint.
Trust me, with a name like mine, I get called all kinds of things, and I don't really care that much.
No, I'm confused because you said just to be a dink. I thought you were dinty,
I am.
not dinky.
Dr. Musk is preferable, though, in chemistry classes.
What's dink? What's a dink?
A dink or a dingus, like somebody that's just trying to stir up trouble. I don't know. I'm trying to stir up trouble by adding this one to the list. I'm
Okay.
intentionally being a provocateur.
Okay. I genuinely wasn't familiar with that word. That's why I was asking. Sorry. Okay.
Do you guys get the same thing that I did for germanium's shorthand electron configuration?
Yes.
Yep.
So
Don't
if
know
you
how to
did,
do this.
how many valence electrons does germanium have looking at that electron configuration?
4.
2.
Remember that valence electrons are any electrons in the outermost shell.
Oh, it's 4.
So those 2 electrons in the 4s subshell are 4th shell electrons. Those 2 electrons in the 4p subshell are also 4th shell electrons.
What's the AR for?
In order to shorthand electron configurations, we also have to give a shortcut for all of the other electrons that are in germanium. So the way we do that is by going back to the previous row's noble gas and just including that in brackets. So that germanium has all of the electrons in argon's electron configuration plus 4s2, 3d10, 4p2. So it's a way of
There's-
summarizing all the stuff before that last row of the electron configuration.
Can't you tell it's just that they're all argon?
Let's try tin. So tin, if we were summarizing all of the stuff before tin's row, which is the 5th row, we would say that tin had all of the stuff that krypton has, all the electrons that krypton has, plus 5s2, 4d10, 5p2. And hopefully you would agree with me that that would mean that tin would have 4 valence electrons. Note a couple of things here, because this is an important thing for us to remember. Germanium and tin each have the same number of valence electrons. They are also in the exact same column on the periodic table.
Imagine that.
That's very important. Also, that group of elements happens to be group 4A. So this is a trick that we can use for any of the main group elements to remember how many valence electrons they have. Main group elements, if you don't remember from your periodic table tour, are the elements over here in the S block and over here in the P block. Those are the main group elements, all of those together. And that includes hydrogen and helium also, all right? So the D block and the F block are the only ones that are not part of the main group elements. For any main group element, we can look at its group number, the one with A after it on our periodic table, and that will tell us how many valence electrons that element has. It comes right from the electron configuration, but if you don't want to write out the shorthand electron configuration, for any main group element, just look at the group number. 2A, that means that any element in this column has to have exactly 2 valence electrons. So if that's true, then let's look ahead to our example, sulfur. All right, if you haven't done your example sulfur yet, looking at the group number, sulfur is in group 6A, we would expect sulfur to have 6 valence electrons. Let's do the electron configuration, the shorthand version of it, and see if that's true. By the way, it's true. So for sulfur, we go to the end of that previous row and see that sulfur has all the same electrons that neon has in it, plus When we get to the third row, we go 3s2 and then 3p4. If I add up all of the electrons in the outermost shell, which is the third shell for sulfur, I get 2 plus 4, 6 valence electrons. So hopefully this is making some good sense. I'm going to leave bromine and potassium for you guys to do on your own, so we don't spend too much time like going over something that is already comfortable. But I do want to look at titanium now, because titanium is not part of the main group of elements. It's a transition metal. So can somebody give me the last row of titanium in terms of its electron configuration? Somebody help me out with that? So it's got all the stuff that argon has plus what?
We like 4 spots into the D block. I don't know if that helps with anything.
4 spots into the D block or just 2?
2.
Okay. So
4 spots in is
what are those last
chromium.
4 electrons? Where are they at?
4s2, 3d2.
Good. So how many valence electrons does titanium have?
2.
Yes. Now, I will tell you that the way we are defining valence electrons, as in outer shell electrons, is not always the way that that ends up working for transition metals. Sometimes transition metals can use some of their inner shell d electrons to react with other elements. So titanium, one of the ways that titanium can react is by using these 2 electrons and giving them away and becoming titanium 2+. Sometimes titanium can also give away these 2 electrons in the 3D subshell and become titanium 4+. For our class, we are going to go with a very strict definition of what constitutes valence electrons. And that is, we're going to say that valence electrons are the electrons in the outermost shell. So for titanium, and guess what? For literally every other transition metal on the periodic table, the right answer for how many valence electrons those have is 2. Let me give you an example.
Wait, actually,
right.
no. The pasta I got last time. Thank you.
So this example is actually an example that's even bigger than any of the elements that we ever look at on the periodic table. I want to look at mercury, all right? We could even go down to meitnerium if we wanted to, but mercury will work fine for the purposes of our discussion here, all right? So I'm going to fill in the shorthand electron configuration for mercury. You guys don't have to do this, but I'll show you what it looks like, all right? So mercury is in the 6th row, which means that it has to have all the same stuff that xenon has in it. I can't fit everything that I want to fit on the screen at once. All right, it has to have all the same stuff that xenon has in it, plus in the 6th row, it will be 6s2, 4f14, whoa, there's that big F subshell, crazy, and then 5d10. How many valence electrons do you see in that shorthand electron configuration? What is the outermost shell of electrons for mercury? It's the 6th shell, right? Only those 2 electrons are outer shell electrons for mercury. So mercury would have 2 valence electrons according to our definition for how we define valence electrons. So any transition metal, if I ask you on an exam, how many valence electrons does that have? It's got 2. And the reason why is when we do the electron configuration, only those s electrons end up being outer shell electrons, and the other ones are in inner shells instead. Olivia, can you summarize the YouTube link that you just sent?
Periodic table song.
Oh, thank you. So I wanted to moderate a little bit, because if it was something about valence electrons, if you're talking about a more advanced chemistry class, they sometimes define valence electrons as electrons that are used to react with other elements. And in that case, sometimes we use more than just the outer shell electrons. So I am being completely honest with you guys in telling you that our definition is not a whole truth. It's just a truth that we're using for now. All right?
Mm-hmm.
There. So I've said my piece about that. The last thing that I want you guys to remember, well, I mean, there are lots of things you'll have to remember, but the last thing that we're going to talk about today is the difference in how metals and nonmetals react to make our first kind of compounds that we're going to talk about in this class, which are ionic compounds. So ionic compounds have to have ions. So ions are atoms that have a net charge. Now, where do those ions come from? Well, they come from atoms. All right. So how does an atom turn into an ion? Well, it depends on whether we're talking about a metal or a nonmetal. So for metals, so metals become ions by losing their valence electrons. This is an oversimplification. This trend works for a lot of metals and almost all of the main group metals. Transition metals are weird though, all right? Because of those d electrons, we can't always predict that the charge of a transition metal is going to be +2, because it's not always that way. If every transition metal had 2 valence electrons and all of them became ions by losing their valence electrons, we would expect every transition metal to end up with a +2 charge when it became an ion. That's not true. All right? I'm just telling you that in advance. For the main group metals, it's mostly true. So let's look at a couple of examples of this. An example, a classic example of the first ionic compound that most students are exposed to is sodium chloride. We get ionic compounds by putting together metal ions and non-metal ions. As a matter of fact, ionic compounds are what we get when metals and non-metals end up reacting with one another. All right? So let's think about how sodium and chlorine react to make sodium chloride. Sodium has how many valence electrons based on where it is on the periodic table? Remember, sodium is in group 1.
1.
So we would expect it to have 1 valence electron. If that doesn't make sense, think about its electron configuration. It's got all the same crap that neon has in it, plus 3s1. That is sodium's shorthand electron configuration. That single electron, the 1 electron in the 3s subshell, that's sodium's only valence electron. It's got 1. So how does sodium become an ion when it becomes part of an ionic compound? It loses 1 electron, its valence electron. So when it loses that electron, it ends up with a net charge of +1. Now, nonmetals, if metals lose electrons, then in order for an ionic compound to happen, something else has to pick those electrons up. Nonmetals are the things that pick them up. So let's look at chlorine on the periodic table. Chlorine is in group 7, which means that chlorine has 7 valence electrons. So in order for chlorine to have 8 valence electrons in its outer shell, it's going to have to gain 1 electron. So gaining 1 electron gives chlorine a net charge of -1. Another way that students really like to think about the charge of nonmetals is thinking about nonmetals gaining electrons until they become like the noble gas at the end of their row. So in order for chlorine to become like argon in electron configuration, it would have to gain 1 more electron to have the same electron configuration as that noble gas argon. For example, oxygen, a group 6 element with 6 valence electrons, by the rule that I wrote down, it would have to gain 2 more electrons to have 8 in its outer shell. That would make it have the same number of electrons in its outer shell as neon, the noble gas at the end of that row. So where do we get the formula NaCl from? The other big principle that we'll learn a lot more next week is that when we make an ionic compound, the positive charges and the negative charges have to balance each other out. We have to have just as much positive charge as we do negative charge. Well, it's really easy when we're talking about putting things that are +1 together with things that are -1 in charge. They're already balanced. We have just as much positive charge as negative in this formula. So that is the formula for NaCl. Now, when we write this ionic compound, students sometimes find it hard to remember that Na still has a plus charge in here. Cl still has a minus charge in here. The reason we don't write those charges is because they have balanced one another out. All right, those charges are still in that ionic compound. We just don't write them anymore because they have balanced one another out. So let's look at another example of making an ionic compound by thinking about what charges the metal ion and the nonmetal ion will have. All right, let's try aluminum fluoride. Aluminum fluoride. So think about what metals do when they become ions. What do nonmetals do when they become ions? Aluminum, the metal here, remember metals are on the left-hand side of this stair step. So aluminum's the metal, fluorine is the nonmetal on the right-hand side of our little stair step. Metals lose their valence electrons when they become ions. So how many valence electrons does aluminum have to lose?
1.
Looks like aluminum is in group 3 out of the main group elements. So it has 3 valence electrons to lose when it becomes an ion. So when aluminum is part of an ionic compound, we would expect that its charge would be +3. Fluorine, the nonmetal, is going to gain electrons until it has 8 in its outer shell. Well, being that it is a group 7 element, it already has 7 electrons in its outer shell. So when it becomes an ion, it does that by gaining just 1 more electron and ending up with a charge of -1. Remember when we write charges on atoms, if it's a +1 or a -1, we just write plus or minus, all right? Not 1 plus or 1 minus. I'm just the messenger, don't shoot me. So how do we combine aluminums with +3 charges and fluorides with -1 charges to make the correct formula for aluminum fluoride? If I put together an aluminum with a +3 charge and a fluoride with a -1 charge, those charges don't balance out. We have a net charge of +2 then. How can we mix these ions together so that we do have charge balance? Olivia and Jules both, I saw Olivia first.
Put 3 fluoride.
Yeah, if we have 3 of those fluorides that are each a -1, then we have a +3 total for aluminum and a -3 total for those 3 fluorides. So the correct formula for aluminum fluoride would then have to be AlF3. This all comes right out of the electron configuration of these elements on the periodic table. The electron configuration is how we can tell which shell and subshell the electrons are in. Now for us, the shell is the important part. For chemists that do even more sophisticated work where we have differing definitions of valence electrons, subshell is really important too, all right? So how ionic compounds form definitely stems right from the electron configuration of those metals and nonmetals on the periodic table. Let's look at one more together, all right? I want you guys to try and figure out the right formula for this ionic compound. Let's do tin sulfide.
That sounds made up, but okay.
It's what we get when we mix tin and sulfur together. Now, if you really know a lot of chemistry about ionic compounds already, you will realize that I've intentionally left something out of this name, all right? There's a reason for that. It's so we can learn about it And also it provides us a nice little transition point into what we're going to be discussing next week, which is like more sophisticated things that we have to think about when we're naming and giving the correct formulas for ionic compounds. So let's just use the basic rules to try and figure out the correct formula for this one. So I've intentionally left something out of this name, all right? I'm lying to you, but I'm telling you that I'm lying to you. Is it better if you lie to somebody and you tell them you're lying to them? I don't know. Sometimes.
Depends on the lie.
I know.
Is it lying if you're just not giving all the information?
It's
I
technically
feel
a
like
lie
I'm
by
lying.
omission in the Catholic Church, but otherwise doesn't matter. It's a
Yeah.
moral question.
Also in the court of law, it's a lie by omission. Anyway,
Which you're not likely to get in trouble for if you're doing it for a purpose that is edifying to the other that you're lying to, but whatever. All right.
Educational purposes.
Yeah. So what do we think in terms of what tin's charge is going to look like when it becomes an ion based on where it is on the periodic table?
did you just ask a question? Because I spaced out. I'm not gonna lie.
I did ask a question.
Okay.
My question was, what do we think tin's charge is going to be in this ionic compound?
4
Based on where
plus.
it is on the periodic table.
4 plus.
4 plus, all right? So the reason why we think that is because tin is a group 4 metal, and metals lose their valence electrons. So if tin has 4 valence electrons, it should lose those 4 electrons when it becomes an ion. So if tin is going to be a +4, what do we think sulfur's charge is going to be in an ionic compound?
+6.
Except we can't have positives and positives put together to make a balanced ionic compound. Sulfur is a
-6?
non-metal, so sulfur doesn't follow the same rules. Sulfur gains electrons until it has 8 in its outer shell. That's how non-metals behave.
Oh, okay. I'm sorry.
It's all right. That's why we're doing this practice.
I haven't hit this stuff yet.
It's a bridge topic. We're getting a little farther than I thought we would today because we were good with valence electrons faster than I thought, which is good. It's all good.
It's okay. It preps me for what I'm about to do this weekend.
So if sulfur already has 6 electrons in its outer shell, because it's a group 6 element, it would have to gain 2 electrons to have 8 in its outer shell. So that means sulfur's charge is going to be a -2. If those were the charges of tin and sulfur, then to balance out, wouldn't we need 2 sulfurs for every tin to have a total of +4 charge for the tin and a total of -4 charge for the 2 sulfurs?
In theory.
Not just in theory, in practice. That's a real formula.
Yeah.
All right. Now, the reason why I didn't give you all the information is tin is a pretty big metal. It's pretty far down on the periodic table. There are some examples, namely tin and lead. Also, indium, I think, can behave this way. There are some examples of metals down here in this part of the periodic table that can actually end up with more than one possible charge. So +4 is a charge that tin can have when it makes an ionic compound. It's not the only charge that tin can have. So the reason why I didn't give you all the information is because in order to correctly name this compound that we just wrote the formula of, because tin is a +4 in this compound, And because tin isn't always a +4, we have to actually be specific about what tin's charge is when we name this compound. Because it's also possible for tin to have a +2 charge in an ionic compound. How would you know that? By looking at the periodic table? You wouldn't. It's a surprise. Do I expect you to memorize every possible metal that can have more than one charge on the periodic table? No. That would be a no. Negative, Ghost Rider. But I do expect you to be able to give me the correct formula if I give you this name where you already know what the charge of tin is. If tin is a +2, and we use Roman numerals for this, I don't know what the history is behind that, all right? There is actually an older way to name these, but you don't have to worry about it. If tin is a +2 and sulfur is a -2, then the correct formula for tin 2 sulfide would have just one of each of those atoms in the formula. So it turns out that tin sulfide is an insufficient name, all right? But I wanted you to think about what we would expect from tin based on where it is on the periodic table. That compound exists. Tin does a lot of times have a +4 charge. It just sometimes surprises us and has a different charge instead. That happens. Another place that happens very, very often is in the transition metals, all right? For example, iron, most common metal that we're probably acquainted with, can very commonly have +2 or +3 charges. Do we have to know why that's the case? No, but we do have to know that iron can have more than one charge and be specific about what its charge is in order to name compounds that have iron in them. So we'll do more practice with naming ionic compounds and also giving the correct formulas for ionic compounds next week. Talking about how to name ionic compounds and how to come up with the correct formula for them, that's all we're covering next week. That's it. It's a lot, actually. There's more to it than we think, all right? But we've gotten the intro because we know where these charges come from. We know that metals lose their valence electrons to make ions. We know that nonmetals gain electrons until they have 8 valence electrons when they become ions, all right? That comes right out of our electron configuration work that we did last time we were together. That's as far as I wanted to practice today. Actually, farther than I wanted to practice, but great. It's good to be ahead. Any questions?
How's your cat?
Which one? I've got 2. Luz, if you're lost, don't worry about it. I'm going to publish the recitation for yesterday before we're done tonight. Also, just go ahead and watch back through the videos at the end of chapter 2. All right, the last couple of topical
I'm
videos
very
in
lost
chapter
right
2.
now, but I know I will catch up with everything.
It's the exam's not tomorrow, right? Chapter 2 is not due until almost all the way through next week, so you have plenty of time. But we're here now and discussing. So if you're lost now, then here, the first time you heard this stuff was right now. Give it a little bit of time to just like stew in the back of your brain, and then watch those topical videos and kind of hear it again in a slightly different way. And you're probably going to pick it up really fast. And if not, then we've got all next week to talk about it too. Okay?
Okay, perfect.
Awesome. Jennifer, I'm going to hand off control of the meeting to you. And then whenever you guys want, you can switch over to your link, but I'm going to hand off control to you for now. Okay? Unless there's something weird that happens and you guys need my help over the next couple of days, this is our last meeting for the week. So have a wonderful weekend. Yeah, I'll see you guys next Tuesday.
Okay. Thank you, Dr. Musk.
Yeah, have a
Bye.
good weekend, everybody.